What's that? So, okay, before flow, what did we learn about? Okay, particle density. Then, how do we measure particle density? Or what are the three different types of particle density we measure? What's envelope density, right? So then, what did we talk about after particle density? Go ahead.
Measurement techniques.
Okay, measurement techniques. Okay, so how do we measure particle density?
Pycnometer.
Pycnometer, okay, liquid pycnometry, gas pycnometry, right? Then after particle density, what did we talk about? Powder density, right? So in powder bulk density, what are the things that we learned yesterday? Hopefully you remember. Man, what did we learn in powder density? Someone murmuring. You don't remember? Hassner ratio, okay, what else? So what, how do we calculate Hassner ratio? Okay, rho T. Okay, tap density over bulk density, right? Or aerated bulk density, right? So, and then we talked about Kawakita and Ludde constants, right? It's related to bulk density and compressibility, right? So what are the different types of powder density that we talked about yesterday?
Bulk density.
Okay.
Particle density.
Okay. In bulk density, what are the different types of bulk density that we talked about? What's that? Okay. Tapped. Compacted, right? So again, their applications are different, right? So, and again, depending on your end purpose, you will have to choose the appropriate density measurements, right? Is that right? Anything else? So how do we measure compacted bulk density? Do anyone remember the name of the instrument? I did not explain much, but it was on one of the slides. Okay. Can you see in your actual testing machine, right? But there is specific instrument called odometer. Okay, so that measures compacted density. Okay, so in powder flow, what did we learn about yesterday? Okay, so what are some of the traditional flow assessment methods, like qualitative indicators? Okay, angle of repose. What is that? Okay, angle of fall. Angle of spatula. What else? Still, there are more.
Differential.
Okay, I'll come back to that. Uniform, yeah. What is that? Yeah, okay, difference in dynamic angle, exactly, yeah, dynamic angle of repose. What else? Compressibility. Okay, so compressibility, that's where we use some ratios, right? So what are the couple of cars ratios that we talked about, or cars flow indicators that we talked about? Yeah, two types. What? Flowability and floodability, right? So flowability, we use 4 different parameters, and then floodability, he used 4 different parameters to get those get those indices, right? So based on the indices, you calculate, qualitatively check the type of flow behavior, right? So what else did we learn? So one more thing, last thing before we end it. Rheometers, yes. So powder rheometer, right? Especially we talked about FT4 or Freeman Technologies powder rheometer, right? So talked about basic flow energy, specific energy, aeration, permeability, etc., right? So again, those are whatever methods that we talked about yesterday. Most of them are traditional qualitative indicators, right? So it helps with ranking of powders, right? We talked about one example, right? Sugar and coffee powder, right? So if you wanted to rank sugar and the flowability of sugar and coffee powder, all these methods can help. One might flow better than the other, right? But the actual flow testing, or math-based flow testing or physics-based flow testing, we do that by shear cell analysis. Okay. Anyone have used shear cell or seen a shear cell? Shearing device? No? Okay. Oh. Okay, so we measure the powder's yield strength. Okay, so yield strength means the strength of the powder, how much strength it takes to move one layer of powder over the other layer of powder. Okay, so that's the yield strength, yielding. Okay, moving. Okay, so that's the yield strength. It's a function of the stress. How much load is acting on the powder. Okay, so we measure the strength and stress. Again, calculate their flow behavior using these two relationships, strength and the stress. Okay, and again these are math based, so we can use these values, whatever we are getting from this test, to design hoppers, bins, to rate the flow behavior, comparative purposes. Most commonly, if you are designing a hopper or bin or even a handling device, you should know some, their flow properties. And flow properties means, how you measure using a shear cell. Okay. So shear cell will, go through some of the properties that we will measure, using a shear cell. Okay. So one of the, some of you might have seen this, word, right? Unconfined yield strength. Okay. This is one of the basic parameters that we test using a shear cell. Okay. Not this way, but unconfined yield strength. Again, how much strength it takes to make the powder flow. Okay. So in traditional measurement, you can measure this using a uniaxial testing machine too. Okay. So you compact the powder, okay, and then apply additional stress so that it breaks and it flows. Okay. The breaking indicates flow of the powder. Okay. So that's called the unconfined yield strength. Okay. Unconfined means, again, the powders are not confined on the site, so they are free to flow. Okay. And then yielding, or the point or the pressure at which it yields or flows, is called the unconfined yield strength. Okay. It's clear?
So what is it? So in the side layer, the first layer, and the layer below.
This one?
So in the boundary only, no?
Mm-hmm.
So how does it become unconfined layer?
So this is the compaction process. You compact confining in under confined wall, then you remove these walls. Okay, you see those walls are not here. Okay, then apply more stress or force, and at one force, it breaks.
When we define the period plane, they are removing the plane.
Yeah. So that's again unconfined, right? So you'll have to keep it free. So the boundaries are free. Okay, free to move. Okay.
Sir, here we measure our the unconfined one.
Yeah.
Separate the two layers.
Yeah. So that's what for.
How much force are required?
Yes. So 2 layers means, as I said, for a powder to yield or move over one layer over the other layer. That's the flow, right?
Yield means like?
Yield means flowing, like moving. Okay. So if you for example, if you take about, I'll talk about that in a minute too. If you have a hopper, right? So if you have powder, you're opening the hopper outlet, okay? So then it's unconfined, right? So then the powder has to flow, right? So that's not almost, exactly that's what here, it's correlating here. You're opening the bin walls, bin opening, and allowing the powder to flow, okay? And at what strength the powder flows is what we are measuring, okay? Clear? But again, oh yeah, this is the one. So what do we care about unconfined yield strength? So when we open the bin hopper, okay, so usually the powder has to break free from this bottom layer, right? So the powder has to flow from here, right, from the bottom. So, but due to this hopper dimension, hopper characteristics, there will be some strength in the powder here, right? So this strength of the powder here should be higher than the strength at this arch. So then only it will push the powder down. So that will make the powder flow. Okay. But if the strength at this arch is higher, that's when the flow stops and there will be caking, holding of powder, etc. Non-uniform flow, etc. Okay. Is that clear? Any questions?
So it depends on bulk density or cohesiveness.
Lots of factors. Particle properties and also the Hopper dimensions. Hopper dimension, Hopper angle, Hopper, wall friction, etc. We will go through some of them. Okay.
So which hope we have last week we were discussing about funnel hopper, mass flow.
Yeah.
Which hopper?
Any hoppers. For any hopper, the strength of this powder should be higher than the strength at this layer, okay, for the powder to flow. It could be a mass flow hopper or funnel flow hopper. If the strength here, if it's not well constructed or well designed, then the strength at this arch will be higher.
So it doesn't depend on stagnant. Some funnel flow means stagnant is there.
Yeah.
Effect wavelength.
So I'm not talking about anything flow, anything from here. I'm just talking about this breaking of this layer and flowing. Okay.
So it's depend on flow also and structure also.
Yeah. So flow, structure, yeah, that's what lots of properties influence this.
Yes.
So not only one property. So funnel flow, mass flow, you change the Hopper angle, right? So that's one major parameter. But we are, what we are doing in this shear cell testing is using all these properties, okay, powder properties, how it yields and how it, flows to design the Hopper angle. Okay, so one basic thing that we are designing is designing the Hopper angle. So based on their properties, you can design this appropriate angle so that the strength at this layer is low. Okay, is that clear? But I'll show you some examples, okay, about Hopper design, etc. Okay, or Hopper angle calculation. So one of the again common property that we calculate again from that consolidation or unconfined yield strength is called the material flow function. So material flow function is the relation between the normal stress and the unconfined yield strength. Okay, so normal stress is this stress at which you are consolidating. Okay, sigma 1. Okay, and that's the consolidating stress. And then unconfined yield strength is the stress at which it's breaking or flowing. Okay, so at different consolidation stress, your unconfined yield strength will also be different. Okay, for example, if you are increasing the consolidation stress, then the unconfined yield strength will also be high. Okay, it's clear. Any questions so far? So again, lots of other factors, other than powder property, Hopper properties, environmental conditions play a lot of role. Okay, humidity, moisture content, temperature, etc. Because humidity and temperature makes the powder cohesive, right? So that will affect. And again, other properties, we talked about vibration, right? So vibration affects those, testing or parameters. There are, I will not talk about this, but there are shear cells that can measure the effect of vibration too. Vibration and consolidation stress and the unconfined yield strength too. Okay. So again, again time consolidation is another factor, right? So most commonly we use bins for storing the powders, right, or any granular material. So over a period of time, from its own weight, it adds strength to the powder, right? So that's called time consolidation. So due to increase in time at storage, and also increase in time at storage, many powders cake. You all know about caking, right? We briefly talked about it, right? So caking of powder is a big issue. When you increase the storage time, the powder can cake, okay? And not the eating cake, okay? It's, you all know, right? At least for agriculture student, it's caking is like agglomeration of powders, okay? So it gains strength. Mainly, losing permeability, losing interstitial, air spaces, the powders become more cohesive. There could be some moisture absorption and adsorption, that leads to bridging between particles, and then they can cake too. Okay? And other fragmentation, plastic deformation, chemical reactions, etc. Chemical reactions common if you are storing crystalline solids. Okay? Amorphous solids, unless and otherwise, if the humidity is very high and temperature is very high, you might not see many chemical reactions, but crystalline solids can change over a period of time due to chemical changes. Okay. Any of you have learned about liquid bridging, solid bridging, etc. between powders, particles. It's very common in food powders. If you're working on food, again, just Google and see deliquescence. Okay. Then again, deliquescence is surface melting of food powders. Okay. It's common in food and pharmaceutical powders too. When the powders absorb water, the surface starts melting. And when it starts melting, then it forms, bridges between particles. It forms liquid bridges, then it turns into a solid bridge. Then, caking occurs. Okay. So time consolidation effect also, again we can check by, calculating or determining the material flow function. Again, material flow function is the relationship between consolidating stress and the unconfined yield strength, right? So in general, what we do is, for shear cell testing, okay, what we do is, you take 3-4, batches of powders and put some dead weight over it, okay. Put some 5 kilogram weight in one batch of sample, put some 10 kilogram weight in one, batch of sample. That adds to the load, right? And keep it for some, 2 days, 5 days, a week, 2 weeks, then test their unconfined yield strength, okay. That's what we, commonly do. So increase in time consolidation in general, the unconfined yield strength will also go up, okay. So amount of strength needed to make the powder flow will also go up, okay, due to the effect of time consolidation. Okay, clear? No? Are you here? You're here? Okay. Any questions? Okay, so again, the flow factor that's calculated from the their material flow function. Again, that's the inverse of the slope of material flow function. So MFF is material flow function. So flow factor gives an inverse of the slope. Okay, so it's a ratio between stress over unconfined yield strength. Okay, so we calculate slope by, how do you calculate slope? Y over x, right? So here it's inverse of slope, that's x over y. Okay, so again, based on that flow factor, you can define the powders. So usually if it's around 1, it's very hardened powder, but if the flow factor is high, then it's free flowing. Okay, that means the powder can flow freely in any type of bin. Okay, so you can get that, right? So if the consolidating stress is higher than the unconfined yield strength, okay. So unconfined yield strength, we talked about it, right? It's on the bottom arch, right? So if the consolidating stress, that means the stress within the powder, within the bin, if it's very high, then this strength at the arch, okay, then their flow will be better, free flowing. Okay, so that's again the ratio of sigma 1 over unconfined yield strength. Okay. So again, but if you take any powder, it might not fit in one category. Okay, so it might change their the powder's behavior change based on the consolidating stress and the unconfined yield strength. For example, the same powder, you are dealing with powdered sugar. Okay, so it might be, it might not flow very well at smaller consolidation stresses. Okay, I'm just giving an example, but that might not be right. But if you increase the consolidating stress, then it might go into a free flowing category. Okay, so that's why it's very important to test at different consolidation stresses and at different conditions, so that you can accurately get their flow behavior. Okay, any questions? So this is again by checking the different, that's a very good question. So by checking different powders, okay. So it's arbitrarily designed, if it's less than 1, it will be very hard and it doesn't flow. You can derive this mathematically too. So if the consolidation stress is same as unconfined yield strength, then the arch at the bottom will not break, right, because it has high strength. So that's again almost that criteria. If the consolidating stress is very high than the unconfined yield strength, then it will flow very freely, right? So the powder will break very easily from that bottom. Okay. Any question? So just a quick question. So which powder will have a better flow properties, A or B? B. Okay, great. Any other thoughts? So for this question there is more than 2 options. Okay. So if I said B is wrong, okay, A is also wrong. Okay, any other thoughts? Okay.
Beyond that meeting, where this is meeting, beyond that, that will be writing same.
Okay.
And above that, B will be filled.
Okay, so that's what very important to characterize the powders, right? So it depends on the consolidation stress. So at lower consolidation stress, you can see A will have a better flow properties. You might remember, right? So it's poor flow to free flowing, right? But at a higher consolidation stress, okay, B is having a better flow property than A, powder A, okay? So powder properties and the stress or the type of bin will affect the individual. You have a question? Go ahead. What was the question?
Sir, if we consider like for time, then A is good in flowing area.
No, we are not talking about time consolidation here at all. It's one time, fresh powder, for example. Fresh powder, you are consolidating at different stresses. For example, 5 kilopascal, 10 kilopascal, 15 kilopascal, etc. Okay. So it's not the exact value, I'm just throwing out the number. For example, at 5 kilopascal, consolidation stress, so you can assume a small bin, like 10 kilogram bin, okay. Then the powder A will have a better flow property, okay. But if you're, storing the same powder in a ton capacity, bulk bin, okay, then, B might have a better flow property than A, okay. Just for comparison. So again, so that's again shows the importance of characterizing. Okay, so if you have powder, you'll have to characterize them well to replicate different conditions. Okay. Okay, so then this another example here. Comparing some of this again pharmaceutical powders. So this is lactose. Lactose, again you can see their flow property changing from poor to better, like little bit conditions changing at higher consolidation stress. Okay, but for some powders like sulfate, lactose, etc., they in general have better flow properties, okay, irrespective of consolidation stress. Okay. Okay, any questions before we go on to the next actual testing? So we can replicate all those in instrument. Okay, that's called the shear cell. Okay, so shear cell in this is what it replicates, as we talked about. You test the powder at different consolidation stress and then get the unconfined yield strength. Okay, so it's usually performed as a quasi-static test. That means you have the powder bed fixed, and then when it starts moving, slowly changing from static to dynamic. That's the point that's called, the incipient yield. That's the point at which we measure their stress and strength relationships. Okay. And again, as we talked about environmental conditions, sample preparation is also very important. Okay. So when you pour powder, in a sample cell, you don't want to unknowingly consolidate them, right? Then you are adding more strength like artificial strength to the powder, right, extra strength. So, most of the instruments, you'll have to pour the powder through sieve, shear cell testing, so that it's uniformly filling within the shear cell, the cup or the holder. Okay. And again, the shear cell testing, it helps with calculating the angle of internal friction. Okay. That again, that's a derived property. This is not coefficient of friction, but this is a derived property, and also helps us calculating the wall behavior. Okay. How does a powder interacts with different wall materials? Like if you're storing powder in an aluminum bin compared to a stainless steel bin, okay, how does it affect their flow properties? Yes, their friction properties, their strength will be different, right? You can take aluminum, you can take stainless steel or any other type of steel, their property changes, right? So again, different, it helps with wall effects. So they don't, using shear cells, we don't get the measures directly, okay, but we use Mohr circle analysis. Okay. Most of you would have learned about Mohr circle analysis, right? At least ag engineering students. Anyone remember Mohr circle? No? Agriculture engineers? Suna? Okay. What's that? Yeah, hardness, when you learn, hopefully in second year of your ag engineering, you would have learned in strength of materials class, right? And it's a difficult class, but you all passed in strength of materials? Yes. Okay. And if not, you will not be here, right, if you didn't pass, okay. But I know it's a difficult class, so you would have learned about Mohr circle. So again, for other students, Mohr circle analysis is the analysis of stress and strength on, structural, structure when it goes through some stress and strain, okay. Well, I'll give a brief, note, but we will not go into those calculations here, okay. So it's a typical, shear cell, Jennike shear cell, and again, I briefly talked about it yesterday. So Jennike is one famous researcher who solved most of this, or who derived all these, fundamental math behind this powder flow, okay. And he developed a machine too. So Jennike shear cell, and how does it work is, this is a sample cell, so you fill the powder, okay, and then you apply some normal force, that's a consolidation sigma 1, okay, and then you apply some shear force, that's the force that needed to move one layer of powder over the other layer of powder. So you slowly apply the shear force, and at one force level, the powder starts moving, okay, the instrument starts moving. So that's the point at which we calculate all the other characteristics, okay. So what are the, again, I'll show some more examples. So this is a different type of annular shear cell, a ring shear tester. It's also very common. Schulze, again, this came from Germany. Very similar testing, but you can see kind of small grooves that helps with easy measurement of powders. Okay. One of the challenge will be, again, using larger size particles will be little difficult in this ring shear testers. For powders it works very well, but if you are using like granulated sugar, then you might not get a uniform value. Okay. So how do we draw again Mohr circles? So from the this testing, you get two values, right? Normal force and then the shear force, right? So we use those two, okay? So the applied normal stress and the shear stress, right? But you are applying force, but you will have to calculate stress, right? So how do we calculate stress from force? So force over unit area, right? So from those unit area, you calculate the stresses. So you relate those points, okay? So at different applied normal stresses, you get different shear stress values, okay? And then that line that connects all those points is called yield locus, okay? So above this point, the powder will flow freely, okay, at these conditions. Again, we will go through some of those applications in a minute, okay? So when you get that point, again, you are not getting any meaningful information from those points, okay? So then, using those points and from the yield locus, we draw 2 more circles. You can draw more than 2, okay, but primarily we draw 2 more circles. So I'm showing only half of this here. It will be a circle, okay. So, but when we talk about powder flow, at least it's in 180 degrees, right? It's a plane. So we take half of the circle, okay. And I'm not again going into the calculations, but if you are, for example, studying about twisting of metals and cylinders, then you will have to draw a full circle, okay, more circle. But for powders it's plain, so we half circles, one minor Mohr circle, and the other one will be the major Mohr circle, okay. So the minor Mohr circle, so again these are drawn. Again, most of these instruments now have automated softwares that gets those circles for you, okay. So the minor Mohr circle, you start from the origin and then just touch the line, the yield locus line, and then draw the circle, okay. So that using that origin and just touching the line, you draw a minor Mohr circle, okay. So the major Mohr circle will be touching at the end point of the the relationship between applied and shear stress, okay. So touching the last shearing point, you draw another circle, that's the major Mohr circle, okay. So you draw 2 circles and then you get the other values such as unconfined yield strength. So this will be the unconfined yield strength, so the right hand side of the minor Mohr circle, okay. You get the major principal stress that's acting on the powder at that shearing point or for that yield locus, okay. And also you get the minor principal stresses, okay. Hopefully I have one more picture that will explain this major and minor principal stresses in a minute, okay. So a couple of other points that you get is again cohesion, okay. So the intercept, the value here, the value from origin to this intercept is called cohesion, okay. Any of you remember Mohr-Coulomb law? Okay, so that's C is the cohesion, right? So tau is equal to C plus sigma normal stress, right? So that's the cohesion. Again, I will show the equation for others, okay, in a minute, okay. So that's the intercept here, okay. So that's the cohesion of the powders, okay. And we get effective angle of friction or effective angle of internal friction when you draw a tangent to the major Mohr circle. So you draw a tangent to the major Mohr circle, and that angle gives the effective angle of internal friction, okay. So that's the friction at which, above which the powder will flow, okay. So again, this is not coefficient of friction, but this is angle of internal friction. This is a derived property from material test, okay. Any questions? I thought I have the a figure, but it might be. So if you take an unconfined yield strength, okay. So we know the side is confined, right? Right. When you are applying stress, so this will be sigma 1, right? That's the applied strength, stress that we are applying to compact the powder. So the stress acting on the side walls is sigma 2 here in this Mohr circle, okay. So that will be the minor principal stress. Again, that's helping to compact the powder, though you are not applying any force or stress on the sides, but still due to the confinement there will be stress, some stress acting on the powder. So again, this is sigma 1, again that's the end point of major Mohr circle, and then the starting point is sigma 2, okay.
Sigma 2 is acting due to the compaction of the powder, right?
No, from the side walls, from the side wall, okay. So the pressure from the side wall during compaction, because it's confined, right, it's not moving, so there will be some stress that acts on the powder to compact. Any questions?
After compaction, we move it, but unconfined is
Yeah.
removing the wall.
Yeah.
So how do you know that the powder is compacted and now we can go for the unconfined test?
So it depends on the powder. You will have to make sure it's compacted. So you should, by trial and error. Okay. So you might, if it's difficult to compact, then you'll have to increase the pressure.
It may fail if when we remove the wall.
At smaller loads it fail, but at higher loads it usually forms a compact. Okay.
By trialing
Yeah.
jams.
Yeah. So in general, what we'll talk about that selection of stress too. In general, it's related to your bin size. So if you are storing in like 10-ton bin, then you'll have to pick some distances within the bin and choose the stress at those heights, and then use that for compaction. But that's those stresses that we will be using here, applied normal stresses too, right? Is that clear? But again, we will talk about that in a minute. Okay. So again, solid fraction. We talked about solid fraction yesterday, right? Yeah. So solid fraction amount of powders, right? So depending on the solid fraction, this behavior might change initially, at least at the initial points of compaction. Okay. So again, solid fraction is the amount of solids present within that sample, right? Within that amount of sample you take. Okay. So sometimes if it's a loosely packed powder, not sometimes, most times, if you're just putting the sample in the shear cell and then start shear testing, the powder might compact, okay, and again that might lead to wrong results. But again, for initial stresses, I'll talk about that in a minute. Okay, but if it's a tightly packed powder, okay, it might dilate, it might loosen up, okay. And then again, I'll not go into dilatancy. So it depends on the type of the powder. Okay. So the powder or the stress state at which it's not changing any volume, or if the solid fraction is not changing, it's called the critical state. So that's the state at which you measure the shear stresses. Okay. Normal and shear stress. For example, if the powder is consolidated, it takes some time to get to the the powders to reach that critical state, so that you are actually measuring the flow behavior rather than their consolidation or over consolidation. Okay. So again, when you apply those, again under consolidated might behave differently, over consolidated, but sometimes you will see those change in strain when you start applying those shear forces. Okay. Okay, for 5 bonus points for tomorrow's exam. Okay, can you give me one example of powder, okay, or solid material that when when it's tightly packed, it dilates, loosens up. Okay. So dilation here means dilation is the powder will change in volume, but it will not change in shape. For example, if it's in cylindrical form, okay, still the volume might change due to the moving of the particles inside, but the shape remains the same. Okay. Any example, but I'm sure all would have seen that example. Okay, at least 99% of you. Any quick thoughts? Generally, it should be cohesionless, right? If it's cohesive, it might change in shape, right? So that's one clue. So it's not like food powder, okay? That's another clue. It's not a food powder, okay? Food powder also there could go through some dilation, dilatancy, okay? What is that? Do you have answer? Or huh? Exactly, sand. That's very good. It's most commonly it's beach sand. Okay, so if you compact beach sand, then again, so I should give you 5 bonus points tomorrow, right? Okay. So when when you check, you can check, when you go to any beach, if you compact them, using your hands, it might, you will feel that moving of particles inside, but still the volume, you are holding it, right? So the volume doesn't change. Okay. So many powders will go through those dilation, and I'm not included here, but the stress that leads to that dilation is called deviatoric stress. Okay, that leads to that change in, that dilation. Okay. But most common you will see in food powders is this, when you put the powder in shear cell, it might consolidate it a little bit, it might over consolidate before it reaches the critical state. Okay. So how does we test this? Testing procedure, it's very similar to like this compaction process, but here compaction process we will have to change the powder, or compact and redo a lot of times, right? Here also we will have to change the powder, but what we do is you apply a normal stress. You can see that it's over consolidated powder, and this is an under consolidated powder, and it reaches a critical state, and at one point it starts moving, right? That's one, that's usually the pre-consolidation, pre-shear force. Okay. So after you pre-shear, you remove this effect under consolidation and over consolidation. You apply a normal stress, sigma 1, which is little lesser than the pre-shear load. Okay. So when you apply those normal stress, then at one point it starts flowing or moving. So that's again the shear stress that needed to make the powder flow. So you keep on repeating that test, by going to smaller normal stresses. Okay. So again, simple simple measurement. Again, as we talked about, it depends on the solid fraction too. So solid fraction will be changing for some of those shearing process. Okay. So that's why sample preparation is very important, and you will have to be very careful when you prepare those samples for testing. Okay. So at those different shearing points, so again we get the relationship between the normal stress and the shear stress, right? So normal stress you apply, right? You are applying, and shear stress you get from the instrument, right? So you get this yield locus, and then you draw the minor and major Mohr circles, right? Then you get all other good stuff, all other values. And again, usually the final stress is called the endpoint stress, which we use for the major Mohr circle, okay, at which we draw the major Mohr circle. Again, you can prepare at different solid fractions, okay, and then repeat those testings. But again, the material flow function or the yield loci relationship will be different for those different solid fractions. Okay. Any questions? Simple testing, right? So again, simple testing, but it gives lots of useful information for when it comes to design. Okay, design hoppers and bins. So in general, again, we assume this as an ideal Mohr Coulomb material. Okay, so that means the relationship between the normal stress and the shear stress is linear. Okay, again, that's the friction, right? So that's the internal friction coefficient. Okay, so again, my ideal Mohr Coulomb law, the shear stress is related to the normal stress and with the intercept of cohesion, right? So that's one major assumption that we do, when we talk about this shear cell use and shear cell measurements. Okay, but the challenge is most of the again, any food powder or most of the biological materials, they don't behave like an ideal Mohr Coulomb material. Okay, the relationship is not linear. Okay, so why the relationship may not be linear for food powders or biological materials, or any material. In fact, you might see ideal Mohr Coulomb material like glass beads, spherical, like those are uniform in size, shape, and surface characteristics. All others may not follow this ideal Mohr Coulomb law. Okay. Why the regular powders does not follow Mohr Coulomb law? It's not attraction, it's due to the presence of cohesion, inbuilt cohesion between those powders. Okay. So you take any biological material, it could be grains, powders, there will be some cohesion, inbuilt cohesion. Okay. So you might not get a linear, I don't think I have those, yeah, the curve here for one example material. So usually you see a curvilinear relationship. At lower stress, it's non-linear, but when you increase the stress, the stress will overcome the inbuilt cohesion between the material, and then it becomes a linear relationship, right? But at smaller stress, you see a curvilinear due to the effect of inbuilt cohesion between the particles, right? So some example here again, cohesionless materials, very rare to find, but their cohesion will be 0, but for like example of stiff clay, this very high inbuilt cohesion, okay, that affects this behavior. Again, I've given some examples there. So we briefly, okay, this is the picture that I was trying to draw here, okay. So again, we talked about this, right? So we draw two circles, major Mohr circle and a minor Mohr circle. So using those values, you get all other, values, unconfined yield strength, major principal stress, minor principal stress, etc. Okay. So, yes, I indicated, so minor principal stress will be the stress from the walls when it directly relates to the stress from the walls, okay. You can relate to ideal, any bin or hoppers too, right. So the walls will put some stress on the powder, right. So that will be sigma 2 or the minor principal stress. Any questions? Go ahead, think and ask me any question if you have. Is it easy to understand? Okay, go ahead. Yeah, go ahead.
Sir, in two graphs, second graph is starting from near about 0, but in this graph it is starting from C. But in exactly C.
C is the cohesion, okay. Cohesion between the powder, okay. So that's not inbuilt, it's a measured cohesion, actual cohesion between the powder. For example, when you put bulk powder in the bin, okay, so there will be some cohesion between the powders, right, due to the effect of weight or other effect from the bin wall effect, okay. So that's what we're measuring using the C. That's the intercept, okay. So what I said was, for most of the materials, this relationship will not be linear, okay, since most of the powders will have, or any material as we talked about here, will have some inbuilt cohesion, right, due to their properties, chemical properties, etc., right. So that changes this relationship. So at lower normal stresses, the shear stress may not be higher than the inbuilt, stress from the cohesion, okay. So that might not change linearly with the change in normal stress.
When we are doing actually experiments, we get like that.
Yeah, it might be, that's a representative picture, okay, but it might not get exactly same, but you will see some curve.
But we are not getting linear curve.
Yeah.
There will be there. Some more chances is there too.
Yeah, so if it's an ideal cohesionless material, you will get perfect linear. But you see from this graph, it will not be never be linear. It's very close to linear.
We are taking this point only near about that linear line.
Yeah. So closest to linear line. Okay. Yeah, go ahead.
Sir, if it is ideal cohesionless material, then why the intercept is on the graph?
Oh, that's a good question. So this is not for ideal cohesionless material. So for ideal cohesionless material, it will be like this. Okay. Yeah, this is for any regular materials. Okay. It's a good point that you noted. Yeah. Any other questions? Okay. So again, we get the effective angle of friction from the major Mohr circle, right? So that's the angle that makes with the final shearing point, okay, or around that tangent to the major Mohr circle, okay, and then you get that angle as the effective angle of internal friction, okay. So we'll see where we apply this, okay. I'll show some examples too, okay. There's one important property that we measure from the shear cell analysis, okay, the angle that connects with the major Mohr circle, okay. I'm not going into those calculations, but it's a It's a lot of equations inside, and again it will take time too, but it's a simple way. But most of the instruments it gives directly, you don't have to do much math or analysis, anything. They throw, they spit out the numbers when you do the measurements. Okay. So the effective angle of internal friction in general is a weak function of consolidation stress. So at lower consolidation stresses it might change a bit, but at higher consolidation stresses usually they are plateaued, they don't change much. Okay. So this ratio also almost remains constant, okay, just for the angle of internal friction, but other properties will change. So same measurement, we talked about measuring one layer of powder moving over the other layer of powder, right? So for measuring the wall properties, okay, what we do is we use that wall material at the bottom, okay, and then put the powder and then measure the shear force that is needed to move this powder above this wall material. So one side it's wall and the other side is the powder, okay. So you can use and test the different types of wall material that you are interested in constructing a bin out of, okay. So if you are constructing an aluminum bin or a stainless steel bin, take a piece of that material and put it at the bottom of shear cell and then measure the wall friction. But most times the instrument manufacturers, they themselves provide those material samples for wall friction measurement. Okay. So very similar analysis. Your question? Go ahead.
Sir, we are here measuring only friction between wall particle.
No, here it's between the material and the particle. Okay.
Like a lower plate or
So this is the wall material, and then the bulk solid will be above that wall material.
they are moving like that.
Yeah, we are moving. You see, the whole thing is moving. Okay. Any other questions? Okay. So again, for any shear cell measurements, ideally, you might need maximum 5 points. So 5 points of consolidation stresses, okay, and then measure the shear stress and then get the yield locus, okay. But again, I think Schulze developed this table, to that you can use as a reference point to get the pressures that you can use based on the bulk density of the material, okay. So based on the bulk density of materials, you can again use different pressures, and also based on the different sizes of silos, okay. So if you are using a large silo and the material bulk density is higher, very high, then he suggests to start with a 50 kilopascal measurements, okay. Again, that's the anticipated load that you will see, in the top of the bin, okay. Again, that's suggestion, but ideally you will have to calculate the loads within the bins and then use those loads to choose the appropriate normal stresses for testing, okay. So how do we, any other questions before moving on to the next part? No?
Sir, those walls used for the test in the lecture, so these are attached with the surface. I think these are not attached. So when they will move, some powder which have small particle size, they can get out from the.
Usually not, those are very sealed. You don't see that powder going into those under the, sheets very much.
We have to give more load on that.
What's that?
For that we have to give, I think, more load on that.
For the powder to move?
Powder to move also. So powder to be inside those walls, we have to give more load on the walls.
Not clear. So you are saying to confine within these walls? So yeah, you'll have to attach it. It's not loose sheet metal, okay. So you'll have to attach it. And again, instruments, they have good attachment, so that's fixed and they don't move, the sheet metal. So when you apply normal stress and start applying shear force or shearing stress, only the powder moves, okay. So it doesn't, usually doesn't move.
50 kilopascal is the maximum lateral pressure it can withstand on the top or on the bottom?
So it's usually, again, that's a good question again, Usually you can, if you read the Schulze's book, you can start with 50 kilopascal assuming, at the bottom, okay? But you can get anywhere, right? So he doesn't give any clear indication of whether, it's a medium, large, what size, etc. So that's why I said if you have a bin, you will have to calculate based on the, dimensions of the bin and then use it. This you can take it as a starting point, but this is not, fixed on stone or anything, okay? Does that clarify? Okay. So you will have to do your calculation, but it's kind of rough indication, okay? Any other questions?
So mainly it is used for finding thickness of the bin.
No. So how it flows, getting the hopper angle, we'll talk about that examples in a minute, okay? How do we use those properties, okay? Okay. Any other questions? Okay. So how do we, again, talked about this, right? Why grind silos are in any powder solid materials, bins are tall, narrow, but liquid tanks are shorter and wider, right? So some of you gave the answer correct, so I'm not going back. But again, this is Jansen's equation that we commonly use to get the stress and both vertical and the radial stresses in bins. Okay, I'm not again going into the equation yet, but in general, again, the only difference here is K is the pressure ratio. Okay, so it's calculated from the angle of internal friction, right? Anyone remember the formula? Okay, sine phi, it's not sine theta. Okay, just quickly, it's a small correction. That's 1 minus sine angle of internal friction, or that's where we use angle of internal friction, okay, to calculate the pressure ratio. Okay, so you calculate either one of them, and then using the pressure ratio, that's K, you calculate the other stresses, either vertical or radial stresses. Okay, and then again, mu is the coefficient of friction, Z is the height from the top surface. What is that? Some joke? No? No, go ahead, you can smile, but if it's a joke, you'll have to share, okay? So again, D is the diameter of the bin, and then gravitational force. So you can calculate the vertical, ZZ is the vertical stress and RR is the radial stress that acts to the side, okay? So what happens, in a solid, this amount of stresses or forces from the friction above almost, at about this, when this value becomes 3, so their value, the stress values are asymptotic, okay? That means they doesn't change, okay? So approximately, if you have a tall bin above like a meter or 2, again depending on the powder properties, there will not be any vertical stresses. The effect of vertical stresses will be low, okay, on the bin. But again, but if you are increasing the diameter, then the stresses will go up. So that's why we limit the diameter, but just to keep the vertical stresses, low, and the effect on the bin and hopper low. Okay, but for is incompressible liquid, any most of the fluids. So again, we know the equation, right? So rho g height. So with increase in height, the stress also increases, right? Goes up. So again, these stresses independent of depth, and then the surface stresses. So most important parameter here is, at least for particulate material, is the diameter of the bin. Okay, so keep it shorter so that you can get away with a minimum thickness bin wall or strength of bin wall. Okay, for stress field. So again, I'm not going into those stress tensors, but I believe it's available online. If you Google and see Janicke's analysis of Hopper stresses, you should be able to get those stress acting on powders in a bin. Okay, again, the stresses in the mass flow hopper, again, he ideally used mass flow hopper. Since above mass flow hopper, you can see, if you are constructing a funnel flow hopper, it's beyond the region of mass flow, right? Then the powder flow will not be uniform, right? So ideally use the mass flow hopper. So dependent on the angle of internal friction, wall friction angle that we measure using those wall material, and then the hopper wall and the vertical, that's the angle of hopper, okay, or hopper half angle or hopper angle, okay. So how do we get those? I'll give you some example here. So if the angle of internal friction is 50 degrees and the angle of wall friction is 20 degrees. So the good thing is, you don't have to do most of these calculations. So Jenike has done all these calculations and he has developed those charts. So we just have to use those charts and find the appropriate angle, okay, for different types and shapes of hoppers, like if it's a conical hopper, if it's a rectangular hopper. I'm not sure if I have, symmetrical slot outlet hoppers, it's kind of slot at the bottom that opens. So for those different types of hoppers, he has done all the calculations. So you just the wall friction angle, flow factor, and then you can get the angle of hopper, okay. So wall friction, again, get the appropriate wall friction angle, relate to the angle of internal friction here and get the hopper half angle, okay. So it's very easy to use. I think I have an example somewhere, okay. Any questions on this? Easy to use, right? So just get the data from shear cells, directly apply on these charts and get those values, okay. Any questions? Again, same for different shapes of hoppers also. He has developed those charts, which again. Oh yeah, this example again, if the effective angle of internal friction is 40 degrees and the angle of wall friction is 18 degrees, determine the maximum wall angle at which a mass flow can occur, okay. So again, we know that 40 degrees and 18 degrees, right? So you pick the 40-degree curve, okay. Oh no, that should be, 18-degree curve, and then hit the 40 and you get the appropriate angle, okay. So simple and easy way, okay, to find the appropriate hopper angle. Any question? Go ahead, yeah. No question. Prakash, any question? No? Okay, so simple to use, okay. So to avoid, again, we talked about this, right? So avoiding flow stoppages. So if you are not able to use that mass flow hopper, okay, what happens is, again, we talked about this. So the stresses at this, in this region at least, should be higher than the stresses at this in the unconfined yield stress, right? So that this will push the material down and then it's breaking the surface and flowing, the powders are flowing, okay. So in general, that's what we try to find out. So at different levels of the bin, what will be the stresses acting on the powder and what will be the appropriate angle at which there is no unconfined strength building on the powders, okay. So that if you change this, the unconfined yield strength will change and the powder will be flowing freely, okay. Is that clear? Any questions? No? Okay. So again, for a mass flow hopper, again, it's, we went through those examples, right? We can get the hopper flow factor too. So for different angles, we can get those relationships. But as I said, most of the relationships, he has already plotted them. So it's a function of, again, we saw this, right? It's an angle of internal friction, angle of wall friction, and then the hopper angle, right? So it's very similar to material flow factor. It's from the consolidation stress and then the stress developed in the material, okay. So the stress developed in the material is the stress here in that powder region, okay? And then sigma 1 and that's a consolidation stress, and then how much it flows, how much it takes to make the material flow. So Hopper flow function we can again draw for different angle of internal frictions between the powders, in that we can use for getting the, I'm not sure if I'll skip these. Yeah, we can use these information to get the discharge rates too, or Hopper again Hopper half angles too. Okay. I'll skip the example. Same example, if you know the wall friction angle, if you know the again angle of internal friction, you can get the appropriate angle for mass flow. Okay. So if you check this book, Principles of Powder Technology, you will see more examples on this. Okay. So again, yeah. So as we talked about, so he developed for mass flow hoppers. Okay. So he developed those relationships for some areas where mass flow occurs. So beyond that region, so then you can assume the flow will be either funnel flow or it doesn't flow. Right. So at those conditions, again you will have to use those external flow aids like external vibration systems, pneumatic systems, etc. Okay. So if you couldn't design that Hopper angle, then you may not get mass flow. Then you will have to use some external flow aids. So again, he has done these minimum outlet diameter calculations for different RFI sizes on all those Hopper half angle calculations. Okay, I'll not go through those. Okay, so flow rates. You would have heard about Beverly equation and Johansson equation, right? Maybe some of you at least. Okay, so again, I believe it should be in Saha and Singh, by that you use for ARS, right? So for coarse particles, it's very commonly used for coarse particles to get the flow rates. Okay, so fine particles, it's difficult to use these or any type of relationship, because there will be high effect from air, right? If it's very small particle, it can fluidize and suspend in air, right? And there will be high cohesion between the particles too. Then using those relationship will be difficult. Okay. Almost, I'm not going through those equations. Only difference is for Beverly relationship, the units must be in SI units. Okay, then only that equation. He developed using SI units, so you'll have to use again kilogram, meters, etc. So from the outlet size, again, constants and diameter of the particle, you can get the discharge rates. Okay. Same for Johansson relationship. It's mostly used for circular, orifice openings, circular outlets. But again, you can use any type of unit system, but only thing, the units should be consistent. If you are using, metric system or SI system, use the same units for both, for all the constants in the equation. Okay. So again, both equations, again you can say the discharge rates highly depend on the bin opening size by the power of 2.5. So if you increase the size of the bin outlet, then the flow rate or discharge rates will be high, right? So that's why we talked about flooding of materials yesterday, right? So if the outlet size is too high, then the discharge rate will be too high, and then it leads to flooding of powders. Okay. Any questions? No questions? We're almost done with the shear cell. No questions? Okay. So we'll talk about, again, improving flow performance. In particle size affects the cohesive forces, right? Interactive forces, van der Waals forces, static charges build up, etc., etc. So in general, larger particles have a greater inertia and less cohesion, right? For example, if you are working on agglomeration and compaction of powders, okay, you wanted to make them flow through small funnels and small, tubes. The small powders, it'll be very difficult to make them flow through those small, systems, conveying systems. What you have to do is agglomerate them to a larger size, and then you can make them into, other, useful products. Okay. Particle size distribution, so more uniform size distribution, so it will have better flow behavior. So if it's highly mixed particles, then those smaller particles will fit into the wide space between large particles, and then it increases the surface forces, right? Surface interactive forces. So shape also, ideally more spherical particles will have better flow, right? But if it's irregular, then there will be more interlocking between the particles, right? So it's more text. So surface roughness too, there will be higher interaction. I'll quickly go through. So if the surfaces are smooth, then there will be stronger van der Waals interaction. Okay, but if the rough surface, then there will be more electrostatic forces or static charge built between those particles. Okay, so either way, if the particles are small, you will have to deal with one or the other forces. It could be either van der Waals or it could be electrostatic forces. So interstitial air, lower permeability or high, low porosity will affect the powder flow. Right, I gave you one example yesterday, right? Wheat flour unloading, you always see, industry use some additional pipes of air flow through that trucks and containers so that the material will flow because of low permeability. But again, larger permeability or larger white space will be better for flow. Okay? So if you can avoid the size distribution, if you can make them more uniform, then the particles will be more uniform or tighter distribution, then the flow will be easier. Moisture, again, you all know, high moisture, low moisture effect. So when you wanted to measure the flow properties, so it's always better to use some shear cell measurements rather than using Kars indices or Hassner ratio or angle of repose, etc. Okay. So as you have seen, if you use shear cells, it gives actual values that you can use for design, hoppers, bins, and also understand powder flow properties. Again, if the powder does not fit in mass flow category, then usually we come with different ways of improving the flow. Coating the wall with some frictionless material, coatings, or air venting, active feeding, etc. Active feeding is in general at the bottom of the bin. They will have a auger type of system, conveyor auger that pulls the material from the bin. But there are tons of these flow aids or flow instruments that helps with flow from the bulk powder bin. If you Google, you'll at least find more than 100 types of devices, etc. And again, empirical benefits, it helps us rank the materials but doesn't give any much theoretical understanding on that. So I didn't talk about rotational shear cells, but there are annular and Pascal shear cells. So translation is, as I've shown the picture, it moves like this horizontally, translation. Rotational shear cells, it rotates, the top part rotates, so that's the way it works, almost same measurements. And there are tons of standards for powder flow measurements, ASTM, USB, etc., that you can use to calculate these. Lots of books and publications on powder flow. Some of these are Jenike's papers are, if you are interested in powder flow, Jenike's papers are very good. And then Johnson is okay. Yeah, Schulze's book, Schulze and Netterman books are very good, if you understand more about powder flow. Okay. Martin Rhodes' book gives the overall introduction about particle technology, but not much in-depth information. But Netterman and Schulze gives better, math and physics behind powder flow. Okay, that's it for this lecture. Any questions? You can stop, take a break now. Okay. Okay, any questions before we leave for break? No questions? all had tea? Okay. So, you asked about exam, right? So it'll be, what type of exam you want? So you're talking about exam, right? Numerical, no exam? But I think for this class we will have to have an exam, I think. Okay. Maybe I should give an open book, open notes exam, right? No? Hey. What's that? Open internet? Then I should give certificate to internet, right? Not to you, right? I think it will be multiple choice question, okay? So more, my questions are mostly applied, will be applied. I haven't prepared yet, okay? So it will be easy. Okay. Or if you want, like, match the following, all those things, let me know. Or if you are interested in numerical, that will be easy for me. Okay. No? Numerical, how many of you prefer numerical? Some simple density calculation, shape calculation. Only 3 of you are raising hands. How about you guys? Will you be okay with numerical? No? No, I'm asking, yeah. You 3, yeah, and her. So, no, that's okay. Yeah. No, that's okay. I'll give multiple choice question. I haven't prepared yet. Okay. Okay, so any questions from powder flow? Go ahead, yeah.
Entire question will be of MCQ type.
Yeah.
What is the total marks?
What's that?
What the total marks?
Total marks will be, you should ask the total number of questions, right? Maybe 10 or 12. Okay.
That's it.
Yeah, so exam will be easy. Okay. Total marks you can make it up, right? Either 10 or 100 or whatever you want to choose, right? So, okay, so any questions? So, good. Okay, so if not, we'll talk about and coefficient of restitution. Okay, so might be useful for you for coefficient of restitution and friction too, right? So we talked about angle of internal friction, static friction coefficient, etc. Right? So that's used in the pressure calculations, right? We use we will not use angle of internal friction here for most of the stuff except for powder flow and bin design, hopper design, etc. Right? So what are the 2 different types of friction coefficients that we commonly measure? Okay, common types. Rolling is not very common. Okay, so static and dynamic, right? So static again. Static when the material is starting to flow, that's static. Dynamic again when it's flowing, right? So rolling again when it's rolling. We commonly don't measure rolling, but there will be lots of. We'll talk about effects of rolling on other frictions. Okay. So why friction is important? Why we are to care about friction? Why do we have to measure friction of granular materials, powders, anything? Okay, one is flow. What else? No, there is some major effect from friction. Stress, okay, how it affects stress? Or how, don't go into how it affects stress, but how this will influence whatever we do, this friction coefficient. So what is friction? Okay, distance, no, give me the actual definition, not the distance. How do we calculate friction? What's that? Okay, F equal to mu? Okay, and yeah, for normal force, right? So normal force and friction force, right? So now you think, where do we apply that? I've given an example here, car tire, right? So what happens when a tire moves on the road? There will be friction, right? So if there is high friction, what will be the effect on car?
Efficiency will decrease.
What's that?
Car's efficiency will decrease.
Car's efficiency will decrease. You might see more wear and tear on the tire, right? So it comes back to energy, right? So energy required to move any material will a lot, depend on the friction between the materials. Almost 30% of the energy that we spend to move anything, it could be from car or it could be from, bulk material handling, depends on the friction between surfaces, right? So again, you can take any example, conveying belt, auger, pneumatic, flow of materials, almost all places, whenever it's starting to move, whenever we are moving something, then friction will play a larger role, right? So again, almost all examples, seeds and fruits when we are harvesting, the friction will affect their damage, how it damages the fruits, etc. Okay. So again, friction is opposite to relative velocity, right? So again, this high school physics, you all know that, right? So we calculate using simple formula, right? The tangential force or the friction force is proportional to the static friction or dynamic friction, and then the normal force, right? Again, simple formula, and then the proportionality constant, we get there as the friction coefficient, right, or coefficient of friction, right? So in general, F is, the friction force is independent of area of contact, okay? But that's, we'll talk about that in a minute, okay? Again, most commonly, the tangential force, the force it takes to move one surface over the other, depends on the type of the material or nature of the materials that are in contact. Okay? You would have seen, right? So when you are riding a bike, if you ride on a tar road, or if you are riding on a brick road, or if you are riding on a concrete roads, the amount of pedaling that you have to apply will be different, right? Again, unless assuming the slope is same, the friction forces will be different. So that's again from the surface of the nature of the material that's used to pave the road, the friction and the energy will also differ. So when two materials are in contact, we might assume that they are in contact 100%, right? So that's again the apparent area of contact that we commonly use for most example calculations, right? But the real contact will depend on the surface roughness, right? So if it's rough, and again we normally don't get any 100% smooth material, so all the materials will have some amount of roughness, okay? So the surface roughness will change how this material will move one over the other, okay? So what happens is, again, when one surface, for example, one contact on this solid and one contact in this solid, okay, comes in close contact during movement, it initiates a contact, there might be different phenomena occurring when it's moving, okay? It starts from elastic deformation, right? So elastically deforms, but if the normal force is not very high, it goes along with elastic deformation, okay? Forces are high, then you might see plastic deformation, right? Some materials breaking, right? Some materials on one or the other surface will break, and then sometimes this surface or one or the other surface can plow through the other surface. That means there is more shearing of materials, right? So all these actions occur when one material goes or moves over the other material. That's why to overcome these contacts, you will need lots of energy, okay? That's why we spend again lots of energy to again overcome this addition bonding. So if it's same material, then there will be cohesive bonding. If the materials are different, then there will be addition bonding that depends on the molecular level interactions, okay? So that type of chemical composition, for example, on the food materials, will depend or will define these, molecular interaction when two surfaces comes in contact. So once the contact is almost ending, the bonding separates, okay, the addition or cohesive bonding separates, and then there will be some elastic recovery, okay. So, but if there is plastic deformation, then you lose those, you will not regain, but whatever elastically deformed, we regain that, the material regains, right. So in general, if you take a closer look or time and force, you will see a stick slip motion due to tons of different asperities present on the surface of the material. It sticks, there will be bonding, then it slips, regains it, elastic deformation is regained, and then again it sticks, slips, etc. Okay. Just as an example, if tire moves on the road surface, okay, there will be continuous of the stick slip motions, that's occurring, or slip forces occurring on the surface of the material. Okay. So how many of you ate bread this morning? Bread, slice of bread. No one? No one used bread? You all are healthy? So how many of you eat bread, or yesterday or last week? So what did you eat with bread very commonly? Jam or butter, right? So when you cut butter, you will see this. Easy to notice this, the effect of friction, this adhesive cohesive bonding, and then finally shearing on the surface of butter. Okay. Very easy to observe, but other surfaces, you may not be able to observe, but very calm. And another general question: how many of you walked? How many of you visited a snow place, snowy region, Jammu Kashmir, Himachal? Any of you? No. Any? You are? Okay. So, did you walk on ice? Ice? Okay. So why you slip when you walk on ice?
Because friction.
Friction. Why? That's what. Friction. Yes.
Because ice surface and our shoe surface is friction between.
But our ice is solid, right? So why the friction is low?
That time moisture content will higher now. When we suppose I'm pressing the ice.
Yeah.
Some melting.
Okay, that's very good, excellent answer. So when you walk on ice, usually for ice there will be thin layer of water surface. So that's what reduces the friction. That's why when you walk on ice, you slip and fall. But that's all fine. There are some recent findings that said, on top of ice, the molecular, structure is not uniform on the crystalline solid. It's a crystalline, right? So that's why you slip more when you walk on, ice. Okay. Again, coming back, that's again friction effect from the change in molecular level, structure on the surface. Okay. So traditional friction measurements. So how do we measure, right? Many of you would have used this kind of setup, right? Yes or no? For grains at least. So you put some amount of samples that the normal force, right? And you slowly slide the platform. So at specific angle it starts moving, right? The whole container with the grains or materials will start moving, and at the place that at the angle at which it starts moving gives you the coefficient of friction, right? Many of you would have measured, right? So that's very common. Go ahead, you had a question? No. So, or if not, again, if you wanted to measure between grains and a larger granular material to plate, again, same observation. You attach the plate, make the grains move above different surface and get the angle at which you get, the grains are moving, and you get the coefficient of friction. Okay. So again, that's static and both dynamic, right? So you can, at the initial force or initial angle that at which it slightly moves will be the static friction coefficient, and the angle at which it keeps on moving, it will be the dynamic coefficient of friction, right? So what will be one major disadvantage of this setup? What could go wrong? from the grain side, okay, don't think about instrument. Any thoughts?
It does not measure internal angles also.
Yeah, we don't have to worry about internal angle. It's just the
Particle to particle.
particle to particle. Not really. So
On cube shapes, it may not fall.
still, you don't have to fall. It has to just move, right?
The layer of grains, like it may happen like a top layer of grain may fall first, or the bottom layer it may fall, but top layer.
That we are not moving from. Yeah, so that might be, but still that gives a friction, right? So we generally take one layer moving. Okay, that's not a big disadvantage for the method per se. Okay. Any other thought? What happens here at the bottom, at the contact between the grain and the sample? What happens is sometimes this can roll inside, right? So again, we are not accurately quantifying the friction between the surface, but there will be some effect of rolling of the materials. Okay, so we all do this measurement, but may not be accurate. For your research, if you want to measure friction, this may not be the appropriate method. Okay. So another method, we use this Instron or MTS machines. What we do is connect to the Instron testing machine and make the grains move through the surface. Again, this is done by one of my I was talking to some of you, right? We give project works for all students. So this is a third-year level students who did this project on measuring friction of soybeans, okay, or different grains. So you can see the grains are not, only the grains are touching the platform, and then the force at which it moves, right, initially and also when it continuously moves. So same disadvantage is here too. So the grains inside can roll, right? So you are not accurately quantifying the static and dynamic coefficient of friction. There will be more effect from rolling coefficient of friction. Okay, but you get a nice graph. The peak will give the value of static friction coefficient, and once that's the dynamic coefficient of friction. Okay, but again, easy and simple example. So on the instrument side, what could be one disadvantage of this method from the instrument side? Any thoughts? And you can guess something from the instrument side. So you're measuring friction, right? So that's a clue. So what could go, what could be one thing wrong in this setup? Or what, it's not wrong, but what could be one thing that does not give us exact, accurate quantification of friction? Any thoughts? Quick? No? Okay. So you're using a roller here, right? So it adds to friction. So the roller should be absolutely frictionless, so that you are quantifying just the friction of material. If not, you will be adding this friction effect to the grains or to the materials. Okay. Same thing, this wire, it should be very stiff. You cannot use some loose strings and straws, because then you are adding force to move that straw or straighten that straw or string that's attached. So it has to be absolutely stiff when measuring. Okay. Friction measurement by shear plates, again, similar to shear test instruments, you can use shear plates. So there will be two plates. Again, you put the powder or grains inside and move one plate over the other. Okay, and then again you get the forces acting between those plates. And same disadvantage can happen here by the rolling of the material inside. So if it rolls, then your accuracy goes down. Okay, or the old setup that I talked about using Instron, you can move both the surfaces. So you can avoid a little bit rolling effect here. If you're if you're moving both of those across, but still, it's not very accurate method. So some authors modified it a little bit, attached the grains of material that you wanted to measure the friction. Instead of moving those, you move the test material through those grains. Then you little bit avoid the effect of rolling or moving of grains, when you measure the friction. Okay. And again, very similar to the shear setup. So, it's again baffle that goes into it, and the grains, when the baffles moves over the grain surface, you measure the friction. Okay. So, there are tons of friction setup measurements that you can develop and use, but there will be some disadvantages. Again, same disadvantage, you will see those movement of materials or rolling of materials that will affect your friction measurement. Okay. But how can we accurately quantify friction? It's difficult, right? So as the method C. But general, if you're using a tribometer, okay, you might get some more accurate measurements of friction. Right? So tribometer, again, very minute measurement of forces on the surface. Again, this is from one of my past research. So we wanted to measure the friction on wheat kernels. Okay, so you measure the force when the surface moves over the wheat kernels. And again, it's not a large range of movement. It's very small movement, like 5 micron, 10 micron, movement. And then it's kind of back and forth movements, and then you can get friction coefficients. We use the same setup for friction measurements and also wear on surfaces. How much you lose when two surfaces comes in contact, mainly from friction effects. Okay. So again, same setup. From the peak values you get the static friction, and then from the plateaued value or the constant force you get the dynamic coefficient of friction. Okay. Maybe the central lab facility may have this a tribometer here. If you are working on friction measurements, maybe you can check with them. Okay. So it's easy to modify those. Again, in this setup, so my student, most of it, he 3D printed the surfaces and then used them, attached them, and then measured those. Okay. So again, it affects many of those conveyance and energy needed to convey. And when it comes to modeling, it plays a big role. Okay, so you'll have to know the accurate friction values when you are, especially when you are using discrete element method models. Right? Any questions?
So that device that will move like this or harmonic motion?
Usually one direction, but I think depends on the instrument type. You can have both directions too. Okay.
Straight plane, we can measure in straight plane also, or we have to?
No, it's straight plane. So you are just measuring the force, right?
Yes, sir.
So you don't have to incline the plane. So you just have to measure the friction. Yeah? What's that?
Can you explain again tribometer?
For tribometer, it's again, it's mainly used for measuring the wear on surfaces. So for example, that tire companies, metal companies, they want to know how much they lose by wear, right? Or so we modified that setup a little to calculate the friction. So wear means again rubbing of one surface over the other, right? So you rub it for like 1 hour, you lose some materials, you get the wear, or you rub it for like 1 day, then the wear will be different, right? So it basically you can adjust the force acting on the surface, and then you get the friction. So what we did was like what my student did was like he attached some kernels on the bottom of that, and then this is a tribometer that measures the surface that measures the force acting on that surface. Okay, so it kind of moves on the surface and get the forces. Okay. So for grain to grain, what he did was he attached some grains on the bottom of this. Okay, so it's not, I'm not showing the picture. So maybe if you look very closely, you'll see a wheat kernel on the bottom here. So on the blue, below the blue. So attached a wheat kernel on the bottom. You just glue it. and then measure, you can measure, grain to grain or surface to surface that is of interest to you. Okay. So clear?
But in case of powder, sir, which method we follow for accuracy?
That's a very good question. Powder, for modeling or for, use? In general, it's very difficult. Shear plate method is common, okay, for powders. Okay. So shear plate method, these are for larger, granular materials, but shear plate you can use for, powders too. Okay. Any questions? Okay. So there are some references, and let's talk about coefficient of restitution. So except you, how many of you heard about coefficient of restitution? No one. So can you guess what could be coefficient of restitution from this picture? It's more useful when you model, but in actual purposes, go ahead, yeah. Can you guess what is coefficient of restitution from the picture? As I said, you cannot give wrong answers tomorrow during the exam, okay? But you can have wild guesses in the class. Yeah, you have an answer, right? Yeah, that's it.
The energy is decreasing in each.
Okay, yeah, that's the answer. The energy lost. So energy lost during impact. Okay, so I'm just giving bouncing of basketball example. So when you bounce a basketball, when you leave bouncing, what happens? It slowly comes to a stop, right? So it losing energy. By losing energy, coming to a stop, right? So it's important mostly when we model, using different discrete element methods or other modeling techniques, just to see when two particles collide, how much energy is lost. Okay, when two granular material collide, how much energy they lose or how much energy they absorb, and then how it affects their handling and processing behavior. Okay, so the simple way is getting, again, as I said, simple way is measuring the energy before and after collision. Okay, so before and after collision, we get the energy, and then from the energy lost, we get the coefficient of restitution. Okay. Okay, yeah, I don't have that there. So one question. Okay. So what is the major assumption here between the two particles? Depending, the nature of the particles. So we are measuring the collision before and after, right? So what could be one major assumption that helps us getting those loss in energy during collision?
Point of contact.
What's that?
Point of contact.
Yeah, point of contact will be uniform, that we assume that it's uniform.
Elasticity of particle.
Yeah, so it's go yeah.
Plasticity.
Yeah, that's we assume that it's elastic.
Elasticity.
Okay, so if it's plastic, what happens? When during collision, it loses some material, right? So other than energy, we are losing some material. So we assume that it's elastic, and it's normal contact between this. Contact, we assume normal contact. Okay. Measure in general based on the velocity before and after impact. Okay, I'll show you some setups. So using the velocity before and after impact, we calculate the energy lost or the coefficient of restitution. Okay. So in general, at higher velocities, the effect will be 0. The coefficient of restitution will be close to 0. Okay, but in lower velocities, it might different. Okay, so I'll talk about that in a minute. Okay, so energy, again, there are different ways. One is mainly from energy lost and the velocity, right? There are different setups to measure. One is based on impact or collision. So you make the material collide, and from the change in height before and after collision, you get the coefficient of restitution. So the change in height or the distance it travels after collision is directly dependent on the energy it's losing, right? If it's not losing a lot of energy, it comes back. If it's losing energy, then, if it's losing lots of energy, the distance it travels will be very low, right? Is that clear? So you can, there are different modified setups to get from particle to particle or particle to wall surface. So the idea is same, depending on it, how much distance it moves, you get the, coefficient of restitution, okay? Common setup, again, free fall experiments. So what happens is, you make the material drop from a specific height, okay, and you use some high speed camera to get the rebound velocity. Okay, the velocity when it falls from a specific height, and from the rebound, by using rebound velocity or rebound height, you get the coefficient of restitution. Okay, simple setups, right? So what will be one major disadvantage of this setup?
So it is difficult to catch the particle of rebound particle in high speed camera also.
No, you can still catch. It's easy. High speed camera, I know it depends on the FPS, right? For frame per second. If you adjust frame per second,
And one more thing, sir, it change from particle to particle.
What is?
For some particle, it rebound height will be low.
Yeah, so it's not.
It will be high.
Yeah, it will never be the same, right? So that's not a big disadvantage too. So that's what we are quantifying, right? Anyone? Any wild guess? So for example, you are dropping a wheat kernel, okay, from this height. So will it rebound in the same orientation? No, right? So the orientation of rebound can change, right? So that means, that grains can roll, right? So when it rolls or when it changes angle, then you lose some energy for that rolling or changing in angle, right? So we are not exactly quantifying the restitution because some energy is lost with rolling or change in angle. So this is always, it's highly used, but it's not, useful when it comes to getting the actual, accurate coefficient of restitution, okay? Since there will be lots of rolling. Okay. This again, one of my students did for grains. What he did was, like, from dropping experiments, he dropped the grains from specific heights into different bins, and based on the distance it traveled across different bins, he quantified the restitution coefficient. Okay, and he plotted, lots of things. I'm not, maybe you would have seen the paper, but if you see the paper, there are, lots of other calculation that goes in, into that. So based on the average bin number, or how much it travels, okay, again, there will be some rolling too, right? But since the plate is slanted, we thought we are accounting for the rolling a little bit, but still there will be lots of, from, rolling off those grain kernels, but you can get some decent value better than, free fall experiments or by impact experiments, okay? Little better, measurements, okay? But again, the major challenges is, very weakly depends on velocity. So for some effects, for some heights, the velocity effect will be high, but again, over a period of time, when you change the velocity, the effect might be, very poor, or the relationship might be very poor. So when you quantify those restitution, then you may not get accurate values. If you change the height, drop height, or you change the impact height, then you might not see any difference in change in restitution coefficient. Okay. One other challenge will be heat generated during those elastic deformations. So if during impact, there will be some heat generation, right? So if by any chance, if there is some heat during that interaction, then you're losing some energy on heat, right? So you're not accurately quantifying the energy for impact or energy on rebound height. There are again lots of examples on measurements or some published papers. Okay. So how do we measure for powders? Again, I will come back to that question. We can easily measure for large granular material, right? But how will we measure for powders, coefficient of restitution? Any thoughts? How can we measure restitution for powders, small powders? Go back to the example of wheat flour. We wanted to measure the restitution for wheat flour. Any thoughts? Come on, give some answer. No answers? Okay, so I will give the answer. We don't measure. Okay, it's very difficult to measure for small materials. Okay, so we assume. So when you are doing modeling, you simulate with range of restitution coefficient values, and through experimental validation, you find the appropriate coefficient of restitution. For larger materials too, we talked about lots of challenges, right, for measuring coefficient of restitution. So most simulations, when you see those papers, they don't measure. They, do some, calibration of parameters. So, model parameter calibration is also, very important and big. So they calibrate some of those properties, such as, coefficient of restitution, Young's modulus. Young's modulus a little bit, maybe you can measure, not for small materials, but for large materials you can measure. But Young's modulus, coefficient of restitution, Young's modulus, Poisson's ratio, etc., very difficult to measure accurately. So what we do is, you assume some starting value, and then keep on doing simulations and calibrate with some simple experiments, like angle of repose or bulk density measurement, etc. Okay. So when you get the exact angle of repose or exact bulk density same as the simulation, then we assume that the values that we took or used for that simulation will be appropriate. So okay. It's not the accurate method, that's the way we can do. Okay. Okay, so any other questions? There's one more lecture pending, right? So we'll talk about some compact property measurements. Okay. So before going into that, so Prashant, what time is lunch? 1:30. Okay, we have time, some time, right? So next lecture is also not very long; it will be short lecture. Okay. So what's your feedback? What did you learn from this? Not from this lecture, overall. 4 days.
We learned a lot about the particle flow behavior.
Okay.
It was not covered in our MTech syllabus, so we learned a lot about
Okay.
it. If we will go to some industry and also we can apply it easily.
Okay, definitely. Okay. Give me both positive and negative feedbacks too. Okay. So what will be one negative feedback?
Also, there is no negative.
Yeah, that's okay. You can. Hey, don't go that far. We'll start the next lecture soon. Okay. No. Yes. Yeah. Yeah, you can. Yeah, you can stop. Or you that okay? Yeah. Can you get? Okay. Anyways, be prepared. Tomorrow again I will ask about feedback, okay? Okay, so let's get started, okay? So we'll talk about mechanical properties. Okay, so when you talk about mechanical properties, what are some of the properties that will come to your mind? I talked about these many times, here and there, but
Related to force, anything is stress, strain.
stress strain, exactly. So that's where we start. What's Young's modulus? What else?
Hardness.
Hardness. It's very good. Yeah.
Cohesiveness.
Brittleness. Yeah. What is that?
Cohesiveness also we can.
Cohesiveness. It's not a mechanical
Not a
property.
mechanical.
Yeah, but you know,
Ductility.
ductility. Very good.
Elasticity.
Elasticity. What's that? Chewiness. Chewiness. Maybe. Yeah.
Shear
Those
modulus also.
shear modulus. Yeah. Yeah, chewiness, I'm not sure. Is that a mechanical property? I don't talk about that in the class, okay, at least. So maybe it's more in food, right? Yeah. So
Chewinginess and
Poisson's
luminous
ratio. What's that?
Chewinginess and luminous, I think it had.
Okay. Yeah, I don't. That's what I don't know. So might be. Okay. Anything else? Okay. I believe most of it. Most of the properties you all covered. Okay. So one of the challenges, when we talk about, biological materials, at least, they are not isotropic, right? So, but if you are talking about metals and some other, manufactured components, commonly they are isotropic, right? So, if you go in any direction, the properties are same, okay? But for biological materials, mostly anisotropic, right? The properties change based on where you measure. Just for an example, you might know about different types of corn, right? You all know popcorn, yellow dent corn, high waxy corn, high amylose corn, etc., etc., right? So their build of starch inside those corn means maize, okay? You all know, right? So depending on this type of starch, their properties will also be different, right? So their mechanical properties, how the starch is intact inside the kernel will change almost all their mechanical behavior, okay? Even optical properties, etc., okay? So again, for any powders or any granular materials, the properties will change based on orientation, right? If you take a maize kernel, okay, so one side it will be germ, right? The other side it will be more, starchy and protein component, right? So if you measure the properties on one side, it might be different than the other side, right? So properties always differ, and again, other effects from shapes will also play a role. Composition, surface composition will also play a role when it comes to mechanical properties, right? But as said, the most basic stuff that we calculate is stress and strain, right? Stress we calculate from force over area, okay? There are two stresses, right? One is true stress and engineering stress, right? So true stress is divided by the current area. That means when you are compressing or pulling, for example, you take a plastic sheet and pull, it slowly expands, right? But the cross-sectional area is also changing, right? It becomes thinner at the middle, right? So that's what we calculate in true stress. That means we account for the change in cross-sectional area. But engineering stress is you take the original area that you are measuring, and that's it. You will not change the cross-sectional area for calculations, right? Same holds good for strain. Okay, so true strain, again, change in deformation, with the corresponding change in cross-sectional area. But engineering strain is, we commonly don't take the, change in, cross-sectional area during the mechanical testing or mechanical process into those calculations. Okay, so calculating engineering stress and strain is easy, right? You know the cross-sectional area, you know the force, you do that, right? But for calculating true strain and true stress, it will be a little challenging. Okay, true strain, you can use some video recordings. There are some LVDT, what's a linearly variable dynamic, I think dynamic testing instrument that this is a displacement. Yeah, that's very good. Yeah, displacement. Yeah, transducer, right? Yeah, LVDT can use, to measure the change in cross-sectional area and, get the true strain. Okay. So when you take a typical, tensile test means you're pulling it. Okay. So what happens is, again, you can relate to pulling a plastic sheet, right? So what happens, it goes to elastic deformation, plastic deformation. At one point it breaks, right? So initial, when at smaller loads, when you pull that plastic sheet also, it comes back to its original position, right? So that's the elastic deformation. All the, strength, whatever it lost during those, pulling will be regained by the material, right? But when you cross that yield point, okay, or yield strength, okay, there will be more change in cross-sectional area. That means there will be more, again, change in the material behavior, where you will not regain it back. When you lose the, when you remove the stress, you will not regain back its original properties. Okay, that's the plastic deformation, right? Right, you all know about this, right? At least most of you. Elastic deformation, plastic deformation, right? So when you keep on, increasing the stress, and again, you can imagine, pulling a plastic sheet. At one point, it forms a small neck, right, where it starts to break, right? So there will be an onset of necking, and then finally it gives up. Okay, you can, can easily relate, right? You would have noticed, right, when you are tearing something or like pulling something apart. Okay. So this is, again, this is a process when we go, we see when you are applying, a tensile load, okay, or pulling it apart. But if you are applying a compression, load, general, this is a compression, yeah. So you might not see a necking phenomena, right? So when you are, instead of pulling it, when you are compressing it, you may not see a necking phenomena. It just breaks, okay? So it goes through plastic deformation, and finally it fractures, okay? So those two different types of tests will be a little different, okay? Compression and tensile testing, okay? But still it goes through some elastic deformation, plastic deformation, etc. Okay. So, ductile behavior, again, there will be significant plastic deformation in comparing a plastic sheet, right? So when you're applying some tensile load, it keeps on pulling until it breaks, right? But if it's brittle, what happens? It breaks suddenly, right? Like comparing a plastic sheet to a piece of paper. When you pull a piece of paper, it like suddenly breaks, right? So that's what, again, brittle behavior almost the fracture strength and the yield point will be almost same. When you cross that, elastic limit, it breaks, okay? So and we can get this relationship from Hooke's law. Again, Hooke's law, you all know about that we use in spring constants, right? Or getting those spring values. So stress is directly proportional to the strain, and the proportionality constant is the Young's modulus, okay, or the elastic modulus value. Most commonly used for linearly elastic material. So if you have some odd, behavior, odd, relationship between stress and strain, you might not be able to use this Hooke's law. That's why it makes it very difficult to measure Young's modulus for biological materials. The relationship is not linear. Again, yield strength, so stress at which it starts, breaking, and there will be more plastic deformation. That's a yield strength. Again, fracture strength, the sample at which, the load at which it breaks. Okay. So first property, again, Young's modulus, right? Young's modulus, we talked about, it's a relationship between stress and strain. Again, very commonly used to, again, characterize the resistance to elastic deformation. Okay. So we use that linear part in that, stress-strain relationship. So we will not use the non-linear part, just the linear part, and get the, relation between stress and strain, and get the Young's modulus, or obtain the Young's modulus value. Okay. And then again, with smaller E value, then they deflect elastically to a greater degree. That means if it's a spring, the elastic modulus will be low, but if it's a hard material like a compact or something, their elastic modulus will be low. Okay. Okay. So, just quickly, as I just said, if it's a lighter material, then the elastic modulus usually low, and then, again, the values it's for mostly pharmaceutical stuff, right? So there are, again, elastic modulus, it's a material property, right? So the temperature, the humidity, the conditions at which the samples are will affect this elastic modulus values, including, how we prepared the compact. Like what strain rate we use to prepare a compact will also influence this, elastic method. Loading rate definitely, in the strain rate, testing method, etc., etc. Okay. But in general, you might remember the Spriggs equation that we talked about yesterday, right? That we used to get, extrapolated value, right? So one of the major challenges, again, extrapolation to zero, property value, okay? So that will give large errors, okay? So mathematically defining this is little challenging, okay? So humidity also plays a larger role, right? I will not go into those theory. Then again, usually presence of water, loosens those, bonds, stronger, mechanical bonds between the particles in the compact or any material, and then kind of affects the overall mechanical strength and influence the, Young's modulus value. Poisson's ratio. So Poisson's ratio is the relationship between lateral and longitudinal strain. Okay, so lateral, again, how much material moves on sideways or changes on the sideways to overall movement on the lengthwise direction. Okay. So if you take that ratio, you get the, Poisson's ratio. So mostly incompressible material 0.5, it's highly porous material like cork, it's usually 0. Okay. But you might see for some material like polymer foams, etc., you might see a negative value too. So when you pull, that might expand on the lateral direction. That gives a negative value, okay, especially for foam materials. Shear modulus, again, that's a ratio between the shear stress and the shear strain. Okay, that gives the, shear modulus. So it comes into play when your, flow of powders. Okay, so you calculate shear stress, right? Same thing, you can calculate the shear strain, right? The strain needed to make the powder move or powder flow, right? So you get those two properties and then get the shear modulus. Again, there are relationship that relates to Poisson's ratio and elastic modulus to the, shear modulus. I'm not going into the, derivation of this relationship, but this is a simple formulas that you can, relate them. So if you know two of these, you can find the other one. Okay. And as the picture indicates, it's from shearing, one layer moving over the other layer. Okay. So bulk modulus mainly when, compressing materials. Okay. So the change in pressure and the change in volume. So when you are compressing a material uniformly from all 360, angles, so it compresses in, volume. That change in volume over applied pressure is the bulk modulus. Okay. So again, it's in negative direction. So, you might see, negative values. For incompressible material, usually it's high in negative. For easily compressible material, it's low negative values. Okay. Modulus of resilience from based on the elastic energy. So you take the area under the curve till it behaves an elastic solid. Okay, so that's the, modulus of resilience. Okay. So if you take the stress and strain at this point, that's a modulus of elasticity. But if you take the area, that's a modulus of resilience. Okay. So that gives, how much energy it loses and reabsorbs when you are applying some stress and strain. Okay. So it gives that calculation of energy lost during this. Okay. So toughness modulus is until breakage. So you take the area under the stress strain curve until it breaks. So it gives the toughness of the material, right? So how much energy it takes to break any material. Okay, it could be both for compression and also for tensile measurements. Okay. Okay, again, plastic. I'll go back. So can you give some examples of these applications? We talk about examples, right? You all wanted more examples, right? So where do we apply this toughness modulus? Any examples that you can think of? Why do we have to characterize toughness modulus?
To determine like up to what load it can be stable if you want to.
Okay, so exactly. So where do we see those applications? Where do we see those applications?
To differentiate between ductile and brittle, if the modulus of resilience and toughness are same, we can say that this is brittle.
Yeah.
And otherwise it's ductile.
Okay, sure.
Cracking some material.
Cracking. So very commonly, you can use this for milling purposes. Okay, that's a very common example. Okay, so how much energy it takes to mill or break into pieces? Because when you exceed this toughness modulus, then definitely it breaks, right? So it losing the same amount of energy that will needed to break the material, right? So same thing for modulus of resilience too. Okay, any examples of where we can apply modulus of resilience? You would notice this almost every day when you go for shopping for fruits and vegetables, this modulus of resilience.
In polybags.
What's that?
In polybags.
Not poly bags, maybe, yeah, poly bags too, how long you can hold the bag before it breaks, right? So that one. But can you think about any example on fruits and vegetables?
Sir, like how we can keep the fruits and vegetables so that it will not get damaged.
Yeah.
Can help in that.
So exactly for that, so sometimes when you buy apples, you might see some brown spot, right? So how does that brown spot is occurring? From damage, right? Some impact damage, right? Or some kind of abrasive damage, right? So, but if the load that is applied on the fruit during handling is less than this, modulus of resilience, then there will not be any brown spots. But if the load exceeds, or if the energy exceeds that you apply on the surface of the fruit or vegetable, then you will see brown spots. Again, based on the energy that you apply, then the area will also increase. Okay. So again, I'm not giving applications or example, but you can relate to almost everyday thing that we do. Okay, all these properties. Okay. So plastic work is mostly for cyclic compression. Okay, so for example, I'm compressing this material like 100 times. Okay, so when when you keep on compressing, when it exceeds the elastic limit, I lose some plasticity, right? I lose some energy. So the difference between the compression and loading and unloading curve, after it exceeds the plastic limit, is called the plastic work. Okay. So amount of energy or energy that loses in that the material loses between multiple or cyclical compression loads or tensile loads. Okay. So what example you can think of where we apply this?
जैसे बीम होता है ना सर, बीम पे कंटिन्यूसली लोड लगता है, वो बैंड हो जाता है बीच में से.
Yeah, so I'm talking about food materials. Okay, beam, okay. And food, fruits, vegetables, grains. What example that you can think of? Cyclic loading.
Sir,
So
gels or
yeah, gels. Yeah, maybe. What's that?
दो सर.
Dough. So what do you know? Dough. What do what?
Stable sir.
What's that?
Permanently change हो जाता है.
That's more rheologic work than more plastic work. So we are changing the property itself, right, of the the components. Well, that's a good guess, though. Okay. So we talked about apples, right, or some grains, right? So can you think of some examples where we can apply this plastic work to improve the safety and handling or improve the quality of materials? No? Go ahead, yeah, tell,
It's like in grapes.
Uh-huh. Yeah, grapes, what happens in grapes? Don't tell while eating, chewing, there will be plastic work. Yes, there will be plastic work, okay.
Cherries also, sir, we can
So,
use.
all fruits, vegetables, grains, what happens, when you are shipping and handling, there will be cyclic loading, right? There will be load, unloading, when you're shipping, when you're handling, when you're rolling the materials, when you're harvesting, there will be load, then you keep the material idle, then you pack it and then ship it, then there will be load on the fruits and vegetables, right? So there will be always cyclic loading and unloading, right? So depending on the plastic work, again, it can change the damage level in those fruits and vegetables, okay? Or even grains too. Grains, we handle multiple times, right? When it flows from farmer's field to a grain storage, FCA godown or something, it's handled multiple times, right? So it goes through those cyclic loading, okay? So again, hardness, it's the surface resistance to plastic deformation, okay. Mostly we use this when it comes to abrasive damage, like for example on surface of fruits. Again, if you wanted to avoid avoid abrasive damage, the load should be lower than the hardness limit of the surface of the materials, okay. Again, increasing hardness implies an increase or higher resistance to permanent damage, right? So you might know some stone fruits, it's they are very resistant to cut or abrasive damage, right? But if the fruits are soft like grapes or apples, they easily damage, right? Again, very similar to the other properties. Hardness is not an individual property, but depends on other values like Young's modulus, yield strength, and etc. Composition, etc. that influence this hardness. Okay. Couple of hardness testers. This is for compacts. Okay. Mostly used for compacts. When you make compacts, you can compacts, metals, steel materials, material manufacturing, etc. They use these hardness testers. Okay. Again, only minor difference here, in the Brinell hardness measurement, they make a spherical indent. Okay. So they make a spherical indent on the surface of the compact, and then based on the measurement of that permanent deformation and the other force and other dimensions, you calculate the hardness of the material. Okay. Simple formula, simple calculation again. The Vickers hardness is little different. It makes a diamond shape indent. Okay. Just their stress calculations are little different for a round indent, a round hole and a diamond hole. So that's why the values, the calculations will be little different in these two methods. But again, both are most commonly used for testing the hardness of compacts. Okay. Fracture energy, again, fracture will depend on the stress concentrations. So again, if you have a corner or if you have some cracks on the surface of the materials, there will be higher stress concentration around that cracks and around on the surfaces. Okay. So that will be the highest probability or place where it starts breaking. Okay. So that's what we characterize using fracture test. I'm just quickly going through. Okay, creep. Creep, again, it's a progressive deformation. That means you apply some stress, okay, and keep the stress constant, okay, and you monitor the change in strain, okay, how it's deforming, okay. So that's called creep. Over a period of time, the strain might change. There will be primary, secondary, and tertiary creep. But if it exceeds that creep limit, there will be a fracture, okay, or the material, there will be more plastic deformation, right. So it's also highly, again, temperature dependent mostly for compacts and other materials, manufactured materials, but again it depends on other parameters too, thickness, composition, etc. Okay. So can you give one application from fruits and vegetables on where do we apply creep to know their behavior? It's again, think about, we are applying the stress, keeping the stress constant, and we are worried about the strain, change in strain or the dimensions. Okay. You think of one application. Where it will be useful to know the creep behavior. Think about fruits and vegetables, okay, one clue. Yeah, watermelon, where? How exactly?
Where we stack the watermelon.
Exactly. So stacking, not only watermelon, any fruits and vegetables, when you stack, in containers or in packages, what we are doing is the load is constant, right? The stress is constant. We are not changing the stress, but it can deform strain. It can change in dimensions, right? Watermelon will be a little difficult. You need lots of pressure, but other.
They stack too much.
Yeah, but still their hardness, surface hardness is very high. If you stack till a tree level or more than a tree level, then you might see those creep behavior. But for other fruits and vegetables, apples, you take any apple, oranges, you see those effect from creep or constant stress condition. So same, almost opposite, similar concept is stress relaxation. So you compress a material and you keep the strain constant, and you measure how much it's losing, in stress, how much it's adjusting itself to that condition. Okay. If it cannot adjust to that condition, then it will fail. There will be more plastic deformation. But if it can relax to its original position, then the material can be within those elastic limits. Okay. So that's again stress relaxation. There are some examples here. It depends on the material properties. So some relax immediately, some materials will take a lot of time to relax. Okay. For example, watermelon could relax immediately, but for apples and softer fruits, it might take time for them to relax. Okay. Again, these all properties will come into play if you are handling materials. Okay. So wear, again, we talked about wear and friction, right? So when one material passes over the other surface, then one surface could lose some components, right, due to wear. So it's very significant, again, during handling of materials. Maybe for milling, wear is desirable because you want to break the particles into smaller pieces. But for handling and shipping, it's not desirable, right? You want to have the material intact, right? So again, it's very similar to what we talked in friction. So there will be multiple asperities contact between the surfaces, and when it's moving over, one surface is moving over the other surface, there will be stick-slip motion, right? For example, in these asperities, it sticks, and when it's moving here, it's slipping, right? There is no contact between the materials. So again, there are instruments that can calculate the wear. One is, again, we talked about tribometer, right? Tribology testing is common to get the wear strength of those materials. For compact, again, it's a conical asperity tester is common, mainly for pharmaceutical industry. But there are models. If you are again using DEM modeling for breakage, etc., then you will be using some models to calculate that wear. One common model is the Archer-Beard model. Based on the force that you apply, you can calculate the volume of material lost from the surface. Okay. So again, it's again easy calculation. Edge chipping, it's very common in pharma, but I didn't change. But if you are interested, edge chipping is, sometimes when you open tablets, you might see some edges are not uniform, right? It's a big problem in pharmaceutical industry, edge chipping. loosing on, from the surface. But if you're in the future, if you're going to compact, powders, then this will be a problem too. Okay. Do you know why edge chipping occurs? Any thoughts, any guess? Due to non-uniform stress on the edges, there will be higher stress, right? And again, if you do not lubricate well the compaction process, then you lose materials. Okay, so yeah, some standards here. I'll quickly go through the compact testing procedure. Now, for most of these properties, we use this uniaxial compression machine or the Instron testing machine that can get most of the mechanical properties. Now, the basic thing we all know, right? So the force and stress and strain, right? That we can get from this uniaxial compression machine. Okay. Skip this. So hardness in general, it's called the Brazilian test. So it's again mostly for compacts. Okay, you compress the material, and based on the type of fracture, you can assess what type of forces were acting during those fracture. Okay, if it vertically cuts, it's normal tensile fracture, shear and compression, triple cleft. Again, most commonly used in pharma industry, based on the forces, how it breaks into pieces. Okay, and very useful when you come to packaging and shipping. At what type of forces these will break. So tensile testing. So we again this is again we assume that the forces acting on all the sides are equal. So you compress the material. Okay, so the test name says tensile testing, right? Tensile is pulling, right? But how are we applying force? We're applying compression, right? So we assume that the forces on both directions, both compression and tensile forces are equal. Okay, but it doesn't happen all the time. But it's a major assumption that we make, so that it's easier to measure tensile strength of compacts. For sheets, plastic sheets, paper, simple materials, you can just pull them and you can measure the tensile strength, right? But for compacts, hard materials, you cannot pull them, right? So it's very difficult to measure tensile testing. So they develop these methods, like using compression, you measure the tensile forces. Okay. Same application, for testing the tensile forces using 3-point bending. I'm not sure if any of you use 3-point bending. So 3-point bending. So you keep the compactor material on two points where it's held on the top of those two contacts. Okay. So these are the contacts where the compact or any material is kept, and then you measure apply force at the center between those two holding rods or holding things. Okay. You apply force and you assume that the compression force applied on the top is equal as the tensile force that's occurring on the bottom, because the force here is compression, right? But here it's tensile, right? It's extending, it's tensile force, right? So we assume that the compression force applying on the top is equal to the tensile force occurring at the bottom. Okay. So using that assumptions, we calculate the tensile behavior of the material. Okay. Friability, if you're working on compacts, is common. You put some compacts into a friability tester and rotate it for some time. Very common in compacts also, granules, like fertilizer granules or any type of granules. You can see how much material we lose during handling and shipping. So you rotate for some amount of time, and from the amount of sample lost during that rotation, then you calculate the friability. So this again, tribometer testing, pin on disc, same as tribology. So you hold the material and using a pin or disc, you apply the force on top of the material, and from the forces you calculate the other properties, tensile strength, mostly, or amount of friction, etc. Okay, so that's it. Oh, you asked my contact, right? So that's my email ID. You can try. So Okay, so we have about some time for questions from any topic, not only this.
So could you explain about the modeling?
What's it?
Could you explain about DM modeling?
DM modeling. So discrete element modeling is modeling the contact forces between two particles. Okay, so I'm not sure. Let me see if I have a PowerPoint. Let me see if I can connect to my computer there at Purdue. If I can get, I should have lots of presentations on DEM. So it's trying to connect. Let's see. Give me a couple of minutes, okay.